Okay, before coming to the Apollon exponents and one dimensional localization, I would like to make one correction and one addition to the things that I said. There were a question concerning where is the ergodicity in my proof. In fact, there is no, and there is a gap in that proof. So I excuse me please, because I like very much density of states, so I was so eager to go faster to the density of states that I missed the point. Therefore, now this spectral spectral properties. Just I rearranged a bit this small section, properties of ergodic operators in L2 ZD for simplicity, because in that case the proofs are technically much simpler than in general case. When you have abstract operators, you have to take care of a number of technical things. Yeah, so and first I need a kind of lemma, which in fact I proved already. Just let me formulate it in a bit different context. My God. Something very strange is happening with
Nintendo.
okay.
I should not. Probably not here.
Yeah. Okay, now it's good. Because my glasses, no, it's good. So it is good example of very fashionable sync entanglement, yes? Okay. And I need a lemma. Let P on omega is an ergodic orthogonal projection. And P xy omega xy from ZD is B its matrix. Then the rank of P omega, this is just integer number, is non-random and is 0 or infinity depending on whether the expectation is 0 or not. So once more, you have we have a general definition of ergodic operator. In particular, it could be orthogonal projection, yeah, ergodic. This is an assertion about the rank of this projection. It is with probability one, either 0 or infinity. In fact, I proved this fact for you when I proved that the spectrum of self-adjoint operator is a closure of the essential spectrum. But now I would like to do the proof in a bit different way. So the proof is very short. So proof. Take rank rank P. Doesn't matter what is the P. Is just like I wrote before. It is just Pxx, the trace. If it is infinite, then it is infinite. It's finite. It's finite. Yes. Now, from this formula, you see immediately that rank P Ta omega is equal to the rank P omega y Because we know that since it is ergodic operator, I wrote the formula that if you have ergodic operator, then it's just px plus a x plus a, yeah? But you have a sum over all the lattice, therefore you just change variables, etc. Therefore, this is a random variable, but it is invariant random variable. Since our dynamical TA is ergodic, this is constant with probability 1. That is here I use ergodicity. The conclusion, rank p omega is, as I wrote, non-random. Now, as for the proof that it's either 0 or infinity, I gave you the proof. Just since it is not random, just it is equal to its expectation. But in expectation will be either 0 or infinity, as I showed you, depending on whether the expectation of each term, which does depend on x, is 0 or not. So we have these situations that I repeat. If we have a orthogonal projection, which is ergodic, then its dimension either 0 or infinity, with probability 1. Now, applying this to EH, okay, EA. I am about operators, any operator in L2Z. On delta, if we have a self-adjoint operator, we have its resolution of identity, its orthogonal projection, and since this is just a function of our operator, what is a function? Just indicator. Resolution of identity, if I take a function chi on t, indicator of the set delta, it is 1 if t belongs to delta and 0 otherwise, then it is just this function of my operator, evidently, by spectral theorem. Therefore, since my operator is ergodic, we already discussed this. Resolution of identity is ergodic, and we conclude that the rank is either 0 or infinity. That means either there is no spectrum at all, or the spectrum exists, and in addition, infinite number of points. And where there was a gap in my proof? In this trivial part, I said if the interval, the first line was like that, if the interval belongs to the spectrum with probability 1, you have something. But we do not know whether it is possible or not. So the proof was, there was no gap in the proof, but the proof was not about that, in a way, yes. So, and the proof that I gave you, it's a bit, it proves the additional things. It proves that it was written correctly, that the sigma A omega, which is not random, is a support of non-random function, non-random measure, which is just, I remind you that this measure is just the expectation corresponding to my theorem. It's expectation of resolution of identity at some diagonal point. It doesn't matter in which, because there is a translation invariance. You can put not 0, 0, but any XX. So we are finished with this is a correction. Now the addition, which I just forgot to give you, despite that it is very important. The next assertion that sigma AC, sigma SC, and sigma PP are also non-random. That means not only all the spectrum, but all the components, all the spectral types are non-random. But be careful here, because in this place we see the difference between two definitions that I gave: pure point spectrum and the set of eigenvalues. As a rule, eigenvalues are very sensitive to the potential. You change potential just at one point, and eigenvalues could be completely different with respect to. By the way, on the talk of yesterday evening, there was an example. There was operator. You add rank 1 projection. You have all eigenvalues are different. They are in between of initial ones. So the eigenvalues, they are very, very easily moving. But pure point spectrum, it's a closure. So if you have, for example, on interval 0, 1, all rational points eigenvalues, it's quite possible. I can give you an example. But the pure point spectrum will all the interval 0, 1, because it's closure. And this assertion is about the closure. So my intention was just to formulate this result because the proof is a bit more tricky, requires certain technique. But in between these two lectures, after my first lecture, I just read that Professor Anderson will be here next Monday. And I would like to, for that reason, I would like just to outline the proof of this part, which is in fact belongs to him. It is given in different language, and it is mathematical proof, but the idea is from his very first paper, the beginning of all this story. And the proof, you see, from that point, we see that we have to find a function of operator. Somehow, starting from the operator, we have to construct a certain measure that will now would measure not the whole spectrum, but pure point part. And this is a construction which I repeat once more, belongs in fact to Philip Anderson. Let's consider the semi-group, in fact the group which is not any. Anderson was about Anderson model, but not necessarily here. Just any ergodic operator in L2 ZD. So from the point of view of physicists, and it was written in the first paper by Anderson of 58, it is evolution operator of now our quantum mechanical system. Now I take this operator at the points, because it's symmetric as any operator, yes? And now I take absolute value squared. What is it? From the point of view of quantum mechanics, this is quantum mechanical probability, not omega. It's a completely different probability. Quantum mechanical probability for a particle that were sitting at moment 0 at 0, for a particle to be at moment t at point x. Now take a limit. T tends to infinity. In fact, limit doesn't exist, but I'll explain later. In which sense? No, it exists, but in certain sense. What is it? Okay, in the honor of Anderson, I would denote this function. Now I would like to write xy, even more general case. This will be a function of two variables. And at the moment, even it is not important that it is a random operator. I'm about just general spectral theory. And but from the point of view of quantum mechanics, what is this quantity? It's called return probability. That is probabilities that start in your dynamics at moment 0 from x. After infinite time, your particle will be at y.
It's not return it when it's
okay,
x,
but
y.
Return, this is if x equal y, it is return probability, yeah? But now I would like to be a spectral. Before I was just theoretical physics. Now I'm a spectral theorist, yeah? I can prove, assume that A has non-trivial pure point spectrum. Then it could be proven that this is precisely this thing. It is just general theorem, which was the way was known even before quantum mechanics. It was proven in 23, I believe, by Norbert Wiener. It's called Wiener theorem. Okay, so here, excuse me. No, my notation, psi lambda on X, it's eigenfunction, indeed genuine eigenfunction, L2 element, belonging to pure point spectrum, and I take the sum over all spectrum. So I repeat mass in random. It is just effect from function theory, from spectral theory. Yeah, now.
So there is no assumption on A.
Not at all, absolutely.
All A.
The only difference, to be precise, completely precise, I have to replace, you see here I am doing just limit t to infinity. This limit, generally speaking, doesn't exist. I have to make a limit like that. Because there's oscillations just before because of point spectrum. If you do not want spectral theoretic contents of this theorem, it is the following. You have a measure, and you have the Fourier transform of the measure. Take the absolute value squared, make this limit, and you get in the limit the only squares of jumps of the measure, of atoms of the measure. This is the theorem that Wigner proved.
Well, there's some physical intuition, which is that I don't understand the singular continuous spectrum, but
there is no absolutely continuous, neither absolutely continuous nor no singular continuous here.
Yeah, but then you're saying that this does not contribute, and the intuition that physicists have is that the absolutely continuous spectrum correspond to states where they escape to infinity. This is like scattering. You mentioned several times that absolutely continuous spectrum, one should think of scattering. So if I started at the wave packet at x, let it propagate for an infinite time, it will just go to infinity, and so I don't detect it at y. And only the pure point spectrum does not escape, and therefore it's picked out by this limit. So
Yes.
that's the intuition. Is that more or less correct?
Correct, modular two things. First, there is mathematical intuition. It is known as Riemann-Lebesgue theorem of integration theory. If your measure is absolutely continuous, then Fourier transform decays. And the first, there are squares of atoms. But it is not important. In a way, of course, you are right. If there is no pure point spectrum, then the integral is zero. It follows from that, yeah?
What means squares of? You mean this psi square?
No, because what are jumps? What are atoms of the resolution of identity? These are just this function without squares. Just take a spectral theorem. You have a sum over spectrum psi lambda x, psi lambda y, and here there are squares.
Must be squares.
Okay, maybe I even have to write like that, but it is not important at the moment because I do not exclude the. You can always choose pure point spectrum real, therefore it is not serious. Okay. So, but of course, Anderson didn't mention, I don't know whether he knows or not, but he didn't mention Wiener's theorem. He just said very simple thing. What is localization? Localization, that means that after infinite time, your particle will not escape to infinity. Martin, it's up to you. So localization, the particle will stay somewhere nearby. This was his definition of the localization. And now we see that in fact he predicted not complete localization, but just existence of localization. Because localization is not necessarily complete, it could be absolutely continuous component, anything. This quantity doesn't fill other components except this one. And he proves that this quantity is not zero, therefore there is localization.
There is part of spectrum.
Yes. Okay, now to prove the theorem, I will not prove this fact, but since we have a quantity that fills absolutely continuous spectrum, just repeat more or less this argument. And what is important, in fact, of course, you can ask me what you will do with this quantity. These are their realization, the behavior completely unimaginable. But we know from that part that it's sufficient to consider the expectation of this quantity. So you take an expectation of A, X, Y. You do the first things you do. Here the sum over all. Now I make modification. I write the sum lambda times, okay, only eigenvalues in a given interval. I would like to have a local quantity to measure different intervals, yes? So I do this, psi lambda square x, psi lambda square y, and then I make the expectation of this function. Now it depends, I will denote little a, and it depends, of course, on the difference and on the interval. And it will play the role of density of states. Even more formal role, in the sense that if it is not zero, you have the point component. Now the natural question, how to learn that the whole spectrum is pure points. There are no mixing of the components, because you can't exclude, it is still open problem, by the way, that okay, you have a spectral axis. You could have here, for example, point spectrum, and here you can have absolutely continuous spectrum. They could overlap. There is no no general law that forbid this. But of course,
Can it happen for a random potential?
no, but we can't prove that it is impossible. And okay, there is a lot of intuition, but I have no time to
It's
discuss.
unstable situation.
Of course, but unstable with respect to what?
Any perturbation.
No, not any. It's hard moment. But the idea is that if your potential is random enough, you have a lot of realization, and then any. Therefore, you have to assume that potential is random enough. And what does it mean? How fast the correlation could decay to be random enough, etc. Okay, but just to finish, so I take the quantity. So this is my thing. Now I would like to put x, y equals 0, and I would like to sum over all x, this quantity, yeah? Since it depends on difference, I can put y to 0 without, so we have this thing. And looking at the definition, what I am doing, okay, here is now 0, and here I sum squares, but they are normalized. What I did get, I get as a result just psi lambda square at 0, expectation. Now compare this with that formula. In that formula you will have the same. If you have n a delta, what is it? It is the expectation of the sum over all lambdas. This is generalized sum, maybe integral, maybe sum, but in the density of states, because of spectral theorem, I use all spectrum points, not necessarily only pure point, only eigenvalues, yeah? And you have the same story, formally at least. So this makes you this gives you the motivation to call this quantity, this is integrated density of localized states. Not all the states, but only localized states. Yeah? And comparing these two formulas, you see that in general you have, of course, this inequality. Because here we sum over all, here just part. But assume for the moment that we are able to prove that in a certain interval of energies, they coincide. This is complete localization. So you can by using this Anderson function, it is known as an Anderson function or return probability, you can not only prove that there is localization, you can prove that localization is complete if you are able to prove the inequality here. Equality, excuse me, equality. Okay, this is what I would like to add. Now let me return to Lyapunov exponents, and my life now is easier, thanks to Ilya, who did already some part of important things for spectral theory. Okay, let me, now we are about chapter 5, yeah? Lyapunov exponents and spectrum of ergodic operators. Not of ESO, ergodic Schrödinger operator. Because the Lyapunov exponent and the in dimension 1. So we have already the definitions, as I mentioned in my lecture, and then Ilya made it much more precise. We have the notion of characteristic. Lyapunov exponent, which was denoted gamma alpha lambda omega. And we have a notion of the just Lyapunov exponent, which is just you take supremum of gamma alpha lambda omega, and this is already not random, as always in this sense, and this will be important. So it is not random, and this is just the Lyapunov exponent. Yes, and now I would like to repeat the assertion that I'll need, that this is called multiplicative ergodic theorem. In fact, as it was proven first by Valerio Siledits, a friend of Ilya and mine and many other people. And let me make a precision, because I don't know, is it you who wrote Russian name?
Yes.
Let me write Ukrainian translation, not Russian, but Ukrainian translation. Ukrainian translation of Siledits is just herring. Precisely that. In Russian it is different. So it yes. No, to be complete. Okay, so multiplicative ergodic theorem is as follows. So we know we define this as a limit, as a limit of log of the amplitude of the wave function of our Cauchy solution. And this is the existence of the limit. You remember in my lecture I wrote limit in the quotation marks, but now Ilya gave the proof. But I'll need a bit more. I'll need to know that I'll need to know a bit more. Maybe just a moment. I don't remember, Ilya, whether you mentioned that matrices are unimodular. Did you mention? Yeah. Okay. So the matrices are unimodular, and for that reason,
Determinant 1.
Gamma lambda, if gamma lambda is positive, then gamma alpha lambda omega is equal, according to the theorem, plus gamma lambda for all alphas except one particular value quite random, minus gamma for that particular value. Of course, it's clear that not more than one, because if there are two values of alpha where gamma, your decay is negative, then all the solutions like that, because it's equation of the second order. There is no more than one, yeah? And we have this either or our solution, if the Lyapunov exponent is positive, and this will be proven by Ilya. I will assume all the time that this is proven, and it is indeed very fundamental technical fact behind all one-dimensional spectral theory of Schrödinger equation. So if the Lyapunov exponent is positive, then we have a thing which is known as exponential dichotomy. Your solutions either grows exponentially or decays exponentially with the same rate, gamma on lambda, yes? Okay. This is what I need from, so to say, stability theory. And now, this was the first section, which was called just Lyapunov exponents. The next section will be Lyapunov exponents in absolutely continuous spectrum. Okay, therefore, the second section of this chapter, LT and of 1D ESU. Okay, and the theorem is like that. Let gamma lambda is positive for almost all with respect to the Bragg measure lambda of a certain interval. Then sigma AC H omega delta is empty almost everywhere. So there is no absolutely continuous spectrum if we know on the interval for which we know that the Lyapunov exponent is positive on that interval. Okay, how to prove? I'll just outline because it's a bit long. We start from the semi-axis. So I am going to consider the operator which I already introduced, H alpha plus. I remind you, what is it? It is just semi-infinite Jacobi matrix. You have here V1, to be precise, yes, plus tan alpha, 1, 0, etc. Here 1, V2. This is operator that we constructed by using Wild theory. Yes? Spectral theory of which. Now, now we have to compare two facts. The first, see what is going on. Now I have to use the positivity of the Lyapunov exponent. Yes? What was proven by Goldscheid? There was no lambda in his formulas, in fact. He didn't use. He had some matrices. But I have a parameter lambda, spectral parameter. Therefore, he proved that there is a set of realization omega lambda of full measure on which what we have? On which we have the exponential growth except maybe one value of initial condition, alpha naught. Yes, so for all initial condition except possibly one, precisely one in fact, you have exponential growth. Yes, so be careful because there are many parameters and this is important point here. So what I have in fact. So it is proven that if you fix lambda, there is a full measure of realization, but it is not good for the spectral theory. In spectral theory, we fix potential in the very lambda, because spectral analysis is for fixed potential. Therefore, I have to switch from a fixed lambda and omegas of full set to a fixed omega, a certain big enough set of lambdas. There is a statement which is known as the Fubini theorem that said if you have a certain assertion for fixed value of each of a parameter and for another parameter its full measure, then for Lebesgue, then for all for realizations of for a set, let me write because it's of realizations of probability 1, we have the exponential growth of Cauchy solutions for Lebesgue almost all lambdas from delta. So I repeat, lambda was fixed, omega was a set, is a set depending on lambda, but full measure. So I can make things upside down. I fix omega of full measure, and then this Fubini theorem guarantees me that I'll have this fact for almost all with respect to the Lebesgue measures, lambdas, spectral parameter. So I can write now that the R alpha, you remember what is it? It is x lambda omega is e to the power plus gamma lambda x 1 plus I have these statements for, I fix omega, but I know that these are almost all realizations. And for any fixed omega, I have this fact for almost all, for L AE lambda from delta. Yes? So this is one thing. The second thing, recall polynomial bounds that were, okay, I don't remember, day after, before yesterday. So we know that doesn't matter whether your Schrodinger operator is random or not, the generalized eigenfunctions, they grow not faster than square root of x, in fact. So we have the following, that R alpha x lambda omega, doesn't matter whether omega is bounded by C lambda, depending on lambda, x to the power, let me be precise, just a bit, they allow to grow not faster than practically square root. And this assertion is valid for rho plus alpha almost E lambda. So this is assertion with respect to spectral measure, because it's spectral theory. What does it mean that this is assertion with respect to spectral measure?
that means that if you are on the spectrum, then your solution doesn't grow too fast. Now compare these two facts. How to make them compatible? The only way is to assume that there is no absolutely continuous component, the back component, in measure rho. But it is precisely, so by using this 1 plus 2, lead to the conclusion that sigma AC on H omega is absent. Otherwise, I would run to the contradiction. Because I repeat, here the back measure, here is the spectral measure. The back measure is not random, standard thing. This measure is random. And we see that with probability 1, this measure has nothing to do with the back measure. So the scientific terminology statement, rho has no absolutely continuous component with probability 1. It is not yet pure point spectrum. This is why I said that my first lecture discussing the back decomposition theorem, that the singular continuous component is a mostly, at the beginning, it was a kind of nuisance. The main problem was to prove that it is absent. Assume that I am able to prove that it is absent, then I prove localization, at least in the sense that pure point spectrum. And the same story in scattering theory, which is much older than random Schrödinger. The main problem technical is to prove that there is no singular continuous component. There is a lot of papers, quite hard to prove this. Okay, but we can't exclude singular continuous component, but we are able to exclude the absolutely continuous component just because we know that the Lyapunov exponent is positive. And the result, and the drawback of the proof, because we can't pass from the oscillated theorem, which is proven for fixed lambda, we can't pass to the measure rho. It is random. Measure could be tuned with the potential. So we can do it only by using non-random measure. We can apply this Fubini theorem. In fact, you can replace the back measure by any other, but not random measure. But doesn't help too much. So this is the first part of things. And in fact, there is much more complete statement which that in fact you have to prove a converse statement. Myself, I proved that if the Lyapunov exponent is positive, then there is no absolutely continuous spectrum. Assume that there is absolutely continuous spectrum. Is the Lyapunov exponent positive? Yes. The answer is yes. It was proven by Kotani. This was proven by myself. And because of this conversion, we have. Sorry.
What's the theorem?
What
What is the theorem that you state now?
I'm writing. So the theorem Kotani is the following. The sigma AC on H omega is a support of gamma. So absolutely continuous component is just the set of energies for which the Lyapunov exponent is positive. Zero. So sorry, what I have to write? Not support, but null set. Okay. Excuse me. There is certain subtlety in this statement. It should be, I can't write precisely like that. There is a technical, some technical things that I would like to discuss. Because it is not continuous. You see, gamma lambda is not necessarily continuous function. Therefore, this set is not necessarily closed. But sigma AC is closed. You have to make certain closure. But in essence, this is what we have, that the Lyapunov exponent is precisely, absolutely continuous spectrum is a set of energies for which the Lyapunov exponent is zero. By the way, it's good exercise to verify that it is valid for periodic potential. You can define for periodic potential, all the spectrum is absolutely continuous, and you can verify that it is precisely the set where the Lyapunov exponent is zero. Or quasi-momentum is real. Okay, so this is a part of the story related to the, in the second section is Lyapunov exponent, and, oh no, I didn't finish, excuse me. This is the first part. I proved this assertion only for semi-axis, but I promised you to do the axis. So what you have to do, you have to prove, you have to consider now the whole axis. You have to consider now I write my operator H plus, I take a certain alpha plus. Now I write the second operator, semi-infinite to the minus infinity. Not this one, but in the opposite direction. And then, by using these two operators, I can write my operator on the whole line in the following way. Let me describe this. So this will be the following. So I write the only how to write in proper way. Okay, there will be V naught plus cotangent alpha minus. Yes, this is, I am writing the diagonal. V naught, V1 plus tangent alpha plus. Now V2, etc. Here is V minus 1, etc. Here I have to write, this is a diagonal. Therefore, there is one here, there is one here, there is one here, one here. So I am writing the two diagonals on where we have unities because of Laplacian. Now, I would like to write in that way. You see that to get, so I am writing in that way, and to restore my Schrodinger, I have to add the matrix with two ones, to put them here, and the matrix that to subtract this one. Therefore, I have to write on the diagonal minus cotangent alpha minus tangent alpha plus. So I am able to present my Schrodinger operator in the whole line as a sum of this matrix and this matrix. But this matrix is just the direct sum, orthogonal sum of two operators. They do not couple because I removed unities. This is
determine the point where you removed it.
Sorry?
At which point did you remove it?
0, 0, 0.
0, 0.
You see 1, 0, 1.
Yeah, what is special about 0, 0?
Doesn't matter, any point.
Okay, so that's
Because-
arbitrary.
Yeah, because of ergodicity, you can do it in any points. You have infinity to both directions. Where is the middle? No, yeah. Okay, but and now we use this statement. It is from general spectral theory. If you have your operator is the orthogonal sum of two, then it's easy to verify. Just because they do not couple. Just you join. You just make a union of spectrum. Spectrum, all the spectrum, all components also. Yes?
Sigma AC of the union of
Huh?
A plus union of plus. I mean, this is equal to something. It's the
Union of two spectra.
yeah.
You would like to say that it is plus?
Yeah.
Just a moment. Yeah, you're right. Okay, but it does matter, in fact. Plus, maybe I have to explain what is a plus. If you have two sets, the sum of the set is a collection of points where first here, second here. Let me see. I can't. No, I think that it is union. Of course, no, of course, it could be. No, it's union. No, come on. David, it's quite hard to be fast when you are lecturing. Therefore, don't make. No, it's union.
Say that what you're writing is the spectrum of sigma of this direct sum.
If you know that your operator is orthogonal sum of two, then the sigma AC. You are right. Thanks.
Notation is very brief. Okay, now it's clear to everybody.
So now we take as A this operator, as B that operator. For each of them, we prove that there is no absolutely continuous spectrum. By just repeat the same argument to that operator. And the EVI is going to prove that the Lyapunov exponent is the same, whether you go to plus infinity or minus infinity. This is because determinant is 1 of the matrices. So we have written our H as the orthogonal sum of two operators. Each of them has no spectrum on delta, therefore this orthogonal sum also has no, plus rank 2 perturbation. And in the part that was about general spectral theory, I told you that absolutely continuous spectrum is stable with respect to finite rank perturbations. Not necessarily 2, any, even more, even this is trace class perturbations, but even, of course. So we just writing this and using results for semi-axis, we are able to prove that our final result, that sigma ACH on delta is empty. Okay. Let me pass to where to? Maybe here. Yeah, here. Now I would like to prove finally that the spectrum is pure point and eigenfunctions decays exponentially. It's called complete exponential localization. Complete because there is no spectrum except a pure point, and exponential because there is exponential decay of eigenfunctions, which is not necessarily, it could be polynomial, but here it is exponential. So I have to, my third section is LE and the pure point spectrum of 1D ESO or complete exponential localization. But these are just mathematical tricks. We would like to have a lot of words. There is one word which says everything. Okay. Now I can't use this trick. No, first, excuse me, please. I am too fast. First is again start from the semi-axis, like before. So I'm about operator H plus alpha with a certain alpha. What is going on? Now what is our, there were several reasons to show you the proof, the absence of absolutely continuous spectrum, because in that proof we started to play with different measures, to switch on from the Lebesgue measure to probability measure and the spectral measure. And what is the point? We know that for almost all lambdas, with respect to the Lebesgue measure, Lyapunov exponent is positive. But it doesn't mean anything for lambdas with respect to spectral measure, because spectral measure is also random. It could be tuned that you have no this effect. And our goal, what we have to do? We have to switch from the Lebesgue measure on lambdas to the spectral measure on lambdas. And this is in fact what we have to do. And to this end, we are going to use recall. So now the theorem, excuse me. Theorem. Let gamma lambda is positive for L almost E lambda from a given interval over the spectral axis. Then sigma H alpha plus delta is sigma h plus alpha pp. Therefore, if the Lyapunov exponent is positive and you are about the Schrödinger operator on the semi-axis, you have already localization, no conditions. So my efforts to prove absolutely continuous spectrum absence were a bit vain, because in fact we have much more for the semi-axis. We know that the spectrum pure points, therefore no questions, there is no absolutely continuous component. But I need this for certain pedagogical reasons. So I would like to prove this theorem. And this is so the proof, again, when I'm writing a proof, that means an outline of the proof, because I have no time to follow all the details. Yes?
Leonid, for almost every alpha.
Oh, yeah. Oh, thank you very much. Excuse me, I forgot. So for almost every, with respect to the back measure boundary conditions, the spectrum is pure point. This is very important. Yeah. Okay, what we have to do now? I would like to know something about the behavior of eigenfunctions with respect, just measuring the lambdas by spectral measure, not by the back measure. But since we would like to switch to that measure, we know nothing about existence of Lyapunov exponent, because Osseved's theorem says nothing about that. So I have to be careful. I have to introduce now, to be more precise, I have to follow my co-citizen, Professor Lyapunov, and to introduce let me see, not to be, okay, I'm introducing now it's called upper Lyapunov exponent. And likewise, I would like to introduce Liminf, and it's called lower Lyapunov exponent, because I don't know that limit exists if I am not about, if I do not fix lambda. So in general, it is what was done by Lyapunov, because he didn't know a priori that limit exists. He wrote imp sup in inf. Then, by the way, for periodic coefficients, he proved that limit does exist. And then there was French mathematician Perron that constructed examples when Lyapunov exponent genuine one doesn't exist. Therefore, upper limit doesn't coincide with lower limit, etc., etc. So it is a point, and it is important. And now, since I am not sure that, now I introduce gamma bar lambda omega. It will be just supremum over alpha, because I need not alpha, we know, of that thing, alpha lambda omega. And likewise, I introduce, writing the same sup, but gamma minus. Because I'm not sure that it exists. Because I would like now to study the sets of lambdas with respect to spectral measure, not the back measure. And, okay, it is natural thing to introduce a set of points of my spectrum where gamma, the upper Lyapunov exponent, doesn't coincide with the, I repeat, this is a set of lambdas. No, excuse me. What I am doing. Yeah, of course. This is a set on the real line the set of those energies at which we have no regular behavior. There are some wide oscillations because the upper limit is not equal to the lower limit. Therefore, the oscillation, there is no regular behavior, regular asymptotic behavior. Yeah. And now by using the existence of Lyapunov exponent, that means oscillators, we deduce immediately that the Lebesgue measure of this set is 0.
Can I interrupt for a second?
Huh?
Can I interrupt for a second? In the case of IID values, which you discussed this morning, we already know, you showed that the spectral measure has a density. So
we proved that the expectation of spectral measure has density, not the measure itself. Of course, density of states is expectation of spectral measure. This is a very important point.
So we have to go through this switching from Lebesgue.
No, but the assertion about localization is about realization. There is no it is an assertion about almost every realization. Yeah, it's much more subtle. Yeah, but nevertheless, I'll use this fact just now. Thanks for recalling. Yeah. So I repeat. Why? Because we proved that the set of lambdas where this limit doesn't exist is measure 0. I just explained this. It follows from the oscillator theorem. Yes?
The supremum of alphas you take, is it the essential supremum?
Sorry?
Supremum over alphas. Is it in fact the essential supremum with respect to Lebesgue measure or not? Because you...
Here you see there is only, I don't remember, to be frank. I think it is overall. Overall, because otherwise, yeah, overall. Yeah. Okay, so we have that. But it is not too helpful because it's the Lebesgue measure, I said. And we would like to make some assertion about spectral measure. And there is no any connection, serious connection between two measures. The Lebesgue measure was invented by Lebesgue, and this measure was invented by Hermann Weyl. One of them was French, second German. Okay, not a simple story. Yes. Now, okay, but recall now the identity that I wrote, even tried to explain, that the integral 0 to pi on rho alpha plus on delta d alpha is, so we had an identity that comes again directly from Hermann Weyl, that if you have a spectral measure, this is what we are interested in, of this operator on a semi-axis, and we vary boundary condition, then the integral over all boundary conditions doesn't matter what is a measure. This is valid, is good exercise, even for the finite interval, where the spectrum is just discrete. You have this identity. Now, okay, we have an identity. I put now, I don't know which, I am looking, here. I am looking for free space, because I need to keep some, I would like to keep some things. Well, now, by using that, I use this identity for the set S omega. It could be written for any set. What does it mean? You have non-negative thing integrated with respect to non-negative measure, just the back d alpha, it is 0. Conclusion, rho alpha S omega is 0, we beg almost every alpha from 0 pi. What does it mean? That means that now we have what we want. We have the exponential dichotomy, either growth or decay, but already with respect to spectral measure. So I repeat, eigenfunctions, because the solutions now, we are now about solutions that are eigenfunctions, generalized eigenfunctions, because we measure them by spectral measure. So I can write the generalized eigenfunctions are either exponentially growing with the rate gamma lambda, because gamma now exists, or exponentially decaying with the same rate. But they are forbidden to grow exponentially because of polynomial bounds. Oh, where are they? Oh. My God, I deleted precisely what I wanted. Okay, doesn't matter. Doesn't matter. We know that there are polynomial bounds, that there is a priori bound, which was very old, it's from 50s, much before the random Schrödinger. We know that generalized eigenfunctions can grow faster than square root of x. Therefore, the exponential growth is forbidden. What is left? Exponential decay. And it is for almost all with respect to spectral measure. So the spectrum is pure point, eigenfunctions decay exponentially. This is a proof for the semi-axis. And I need to know nothing about potential except that the corresponding Lyapunov exponent is positive. The potential should be such that Lyapunov exponent is positive because two more ingredients of the proof, Oscillated theorem and this identity, they are quite general. Okay, now how to switch to the whole axis? It seems that I can try the same trick, but not at all, because unlike absolutely continuous spectrum, pure point spectrum is very sensitive, and it could be completely different adding rank 1, rank 2 perturbation. Therefore, I have to use something else. Okay, the natural idea, of course, since we can't split our operator, natural idea, just take the measure of the operator on the whole axis and try to average, but with respect to what? There is no alpha now. We have to find corresponding parameter with respect to which we can, that will give us something like that. If we will be able to do that, we are done. Okay, and this is the last point. Now the theorem about whole axis. Point section. This is now the genuine Schrödinger operator is with a random potential, and as we discussed today, since the strong motivation of the random Schrödinger is condensed matter physics, so to have a semi-axis is not sufficient, because that would mean that we are able to study a piece of metal with impurity, but just demi-space, just a piece with a boundary. It's not bad. There is so-called there is a big branch of modern physics called surface physics. But first of all, we are always interested by the bulk properties. Therefore, we have to assume that our space is infinite in all directions. There are no boundaries. Yeah. Therefore, I have to study this operator, and
But you're still in one dimension, right?
yes. I do the. Maybe I have to. Good. Thank you very much. I would like to make a remark about the proof of absolutely continuous component that I gave. I used again general stuff plus positivity of the Lyapunov exponent, and the proof can be easily extended to the multidimensional case where there is no Lyapunov exponent in multidimensional case. But there is another fact that Tom Spencer would like its whole to explain, that Green's function of multidimensional Schrödinger operator decays exponentially in certain directions. Since Green's function decays, if your solution doesn't grow too fast, you are done. So you use the same technique, just replacing positivity of Lyapunov exponent, by the proof that the Green's function decays for a fixed energy. Again, you fix an energy like for the Lyapunov exponent. You fix an energy, you have to prove that Green's function decay. By the way, it's easy to prove by using standard formulas that if you have a Lyapunov exponent positive, then in one-dimensional case, Green's function decays because it's constructed from Cauchy solutions. But in general case, in multidimensional case, there is no Cauchy solution. It's just a completely different story. But nevertheless, I think it is the main achievement of spectral theory in multidimensional case is a proof that Green's function decays in certain domain of the spectrum. In fact, near the spectrum edges. Yeah, okay. Now my goal is to find a replacement of this nice trick. And I remind you that the spectrum measure, I mentioned this fact of H, rho H, can be rho H on delta, is 1/2, can be chosen in that way. This is again the fact from general spectral theory. I have to take resolution identity in 2 points. This is not constructive. Wave theory gives the constructive form of this via the limit of expanding intervals, but you are going to see that this representation, you prove first something that White proved, and then you observe that it could be written in that form. And now, let me recall you the proof of Wagner lemma. This is what you mentioned, Martin, that we proved that if now, okay, now maybe I have to formulate the theorem. Let H be 1D ergodic Schrödinger operator whose potential okay, it's not nice English, such that whose potential, okay, excuse me, is IID. So potential is just independent, identically distributed random variables having bounded probability density. So I take as a potential identically independent, identically distributed random variables, and I assume in addition that probability law, which is common for all values of the potential, has bounded density. Then, if gamma lambda is positive for the bag almost every lambda from a certain set, then we have the same thing. The spectrum on delta is pure point. So just running a bit before myself, I would like to say you that the role of integration with respect to alpha will be integration with the potential, with respect to potential itself. The role of averaging parameter plays the potential itself. So I found the mean inside the operator, not outside like it was before. Okay, now the proof. What I have to do, I have to show what is my goal. My goal is to show, no, I have introduced the sets S plus omega, S minus omega, now for both infinity, for plus infinity and minus infinity. I have to study the behavior of my eigenfunctions when x tends to infinity plus in minus infinity, yes? And I have now two sets. First, concerning the asymptotics on plus infinity. Second, concerning the asymptotic behavior on minus infinity, yes? And by the same argument, that means Archimedes' theorem, conclude that the Lebesgue measure of both sets is 0 with probability 1. This is more or less like before. But now I have to switch from the Lebesgue measure to the spectral measure of this operator, rho h. And to switch, I need the same arguments that we used to prove the Wegner lemma. So what I would like to prove, I would like to prove the following. I take the expectation of my spectral measure. I would like to study the expectation of this measure. In fact, we proved already, yes, but I had to be just a bit more. Okay, maybe we proved already that this is Wegner lemma. There is a constant such that we have this. We even found the constant. The constant here is just the L infinity norm of the density of the probability density of the potential. Now you see, look at the difference. Here we have an exact equality. Here we have an equality, but it's enough. Now I put here delta S plus minus omega, and I find that rho h of S plus minus omega is 0 with probability 1. So on each of two infinities, on plus infinity and minus infinity, my solution either grow exponentially or decay exponentially. But any growth on any of two edges is forbidden by polynomial bounds. Therefore, no choice. It has to decay exponentially on both infinities. And this is what we will, for which set of lambdas, for rho h complete set. Okay, so we have conclusion. Conclusion that all, how to say, rho h, almost every generalized eigenfunction for lambda from delta decays exponentially. So there is no solutions that do not decay. All of them decay exponentially. All of them belong to L2. All of them standard point spectrum. This is all. This is the end of the proof. Now, in multidimensional case, you do the same.
Point. Well, exactly. I'm sure that you have shown it. Well, did you show that this set is not empty
Which set?
of the states, of the eigenstates, the decay exponent
I assume that Lyapunov exponent is positive.
of the states?
Yes,
So the hard part is to show that the Lyapunov exponent is
Yes,
positive. This
of
whole
course.
business.
yes. It's the hardest part. The hard analysis you need for that. All other things you see, okay, it's not simple to just to find, but since it is found, and just to support these words, I would like to say that again, in multidimensional case, you have to prove again, there is no Lyapunov exponent, but you have to prove again that there is exponential decay of eigenfunction for every energy in a certain range of energy which you are able to consider. So far we are able to consider the spectrum edges, and we are able to prove that there Green's function decays. And now having this fact instead of positivity of Lyapunov exponent, and using again the same condition that potential has a bounded density, but now in multidimensional case, you can conclude that there is exponential localization near the spectrum edges in any dimension, doesn't matter which, up to million.
What is slightly strange for me, that it seemed that because you used some strong assumptions for proving Wegner lemma, it seemed that proving localization in infinite setting, in both, somehow it happens under more stronger conditions than on semi-axis. So in semi-axis you in fact proved it.
Yes.
So
it's
it's
true.
It's true.
It's true. It's okay. This is fact of life.
Uh-huh.
Yeah,
Not obvious at all.
but we feel all of them. We feel that there is a lot of space still because look, I made averaging. This we discussed on this morning. To prove the Wegner lemma, I integrate only with respect to point potential at one point. And if I am able to integrate in many points, I can prove more. But I hope that Ilya will show that the positivity of the Lyapunov exponent has nothing to do with existence of the density. Even simpler, if you have Bernoulli potential, it's quite simple to prove that the Lyapunov exponent is positive.
Yet it's not.
Yeah, and by using this fact, it was proven for in one-dimensional case, was proven for much larger class of potentials, but it is hard work. That we have exponential localization. Even in the case where is nothing similar, even in the case when potential is Bernoulli, at which point it is 0 or 1 with probability 1/2. And still there is localization because the Lyapunov exponent is positive. But the technique, of course, much more involved. This is why I have chosen this part, because in essence I explained it to you how does it work. But I use the simplest possible assumption. The potential is smooth. And for physicists who are here, it is simple to understand why we need this smoothness condition. Because what is a localization? You put your particle, you have a potential that fluctuates. Of course, since you have we assume that correlations between values of potentials in remote points is not too far, there are always big wells. The particle will live there quite long time. But at some moment, the particle would like to tunnel in another well, which could be quite far apart. And from quantum mechanics, we know that what is the obstacle to make quantum mechanical tunneling, or resonant tunneling. This is two things. The wells should be as possible different. If the tunneling is the better, the more similar wells are. If wells are the same, tunneling is infinite because periodic potential. Take periodic potential. The eigenfunction is everywhere. It's block function. It's of the order 1 everywhere. The tunneling is through all the crystal because the wells are identical. See, if your wells are different, tunneling is suppressed. And if you have continuous distribution potential, roughly speaking, the probability to have two identical wells is 0. So there is no tunneling. You put your particle somewhere, it will be there forever. This is a simple intuition behind. And when you have, for example, Bernoulli potentials, much harder, because just 0 or 1. You can much easier to make two wells, two identical wells, because just potential takes two values.
Why this reasoning does not work for half line? We also can try to reason
Life is more complicated.
that continuous favors localization, because on half line you do not need it, as you proved.
No, I'm just explaining
Yes.
simple
So I try to
ideology.
understand whether this.
No, but
correct.
no, you assume unconscious is that my intuition is precise, 1-to-1. But I am just explaining you easiest case where things are evident. When you have this Bernoulli potential, you have very complicated tunneling interference between things, etc., etc.
Yes, but you will have the probability of finding a large group that will repeat itself very fast is small.
Yes, yes.
And so I think really it is, this localization is much stronger. So I just don't understand the argument of the continuous potential. For example, if you have these wells and you have the particle with extremely large energy, then it will still be localized.
Once more.
It will still be localized.
If what?
If you have this continuous potential,
Yes.
the kinetic energy is much higher than all the barriers.
This is the same that we discussed with Jan. I am not saying that my intuition covers all the possible cases. I am saying that it is good to it's quite often is good already to understand a certain case. It gives you certain understanding, certain intuition, certain insights. This is what I am doing. I am not doing precisely one-to-one explanations.
We should emphasize once again that although the discussion has focused on potential wells and tunneling between them, or the intuition discussion right now, that we have this surprising fact that maybe I can put it this way: we start from the Laplacian without random potential. It has absolutely continuous spectrum.
Just plain waves.
Plain
Yes.
waves.
Mm-hmm.
Now you're telling us that any finite rank perturbation will not change the situation. The absolutely continuous spectrum is stable. However, now we add a random potential on the whole line. This is no longer finite rank, it's infinite rank. And it makes the spectrum pure point. And it does so for arbitrarily small strength of the random potential. So this is Schmuel. It's something more subtle or more powerful or deeper than sort of tunneling between wells. The classical motion, it's a quantum effect. The classical motion is perfectly happy. The classical particle will just get a little bit accelerated, a little bit decelerated, and will move happily along this line. It's the quantum mechanics that causes it to localize, and I find that absolutely astounding.
Yeah.
Interference.
Yeah, but in fact, this is half truth, because in fact there are two, even on that level, intuitive level, there are two basic mechanisms of localization. First is just trapping into the wells, which is more or less trivial, and this is what I explained. But now explain me, please, by using this ideology. This is for you, Shmuel, that you would not think that I am completely serious about this ideology. Let's take the potential, which was, by the way, was in our first paper with Solchan and Goldscheid. Let's take the potential, which is random, but bounded, say, between 0 and 1, continuously distributed, bounded. And let's take a particle with that energy, much higher than the highest potential. What is going on? Where are the wells? But nevertheless, localization is a mathematical fact, rigorous fact.
But this is interference of backscattering.
Precisely. There is no trapping. There is another mechanism. It's called enhanced backscattering, because the interference, so-called destructive interference of waves. So it is another mechanism.
And what's also probably important, that the wave packets return to the origin with probability 1.
Yeah.
And so
In
therefore,
one
if now... and
But
also
why do they return?
And
Why do they return?
Classically, just it's very
Oh my God.
and then you collect all the phases. And so this is...
I do not agree.
some
This
intuition
is,
of
for
it.
my opinion, it's just coincidence. No,
Coincidence?
I do not agree.
No, because there is a clear semi-classical understanding of how this basically this enhanced.
Is it semi-classical?
Oh,
I'm not sure.
yes, I think it's okay. It depends what you call semi-classical.
Well, it's
You know, I remember when we proved localization, I had very many discussions with Professor Lifshitz, who was one of the founding fathers of disordered systems. He said, I can't understand why do you have localization in that situation? Because semi-classics works. We have propagation if the energy is bigger than the potential. And okay, we discussed a lot, and then I just realized that there is one thing. The potential, random potential is never smooth. Because it is just another side of decaying of correlations. If it is not correlated far away, it can take any values. So basically, random potential is never smooth enough. And for that reason, semi-classics doesn't exist in random Schrödinger. In the sense of Schrödinger. No. It exists in the sense of weak localization, but it's another story, Jan. Completely different story. You count different things.
Leon, you can invent very nice random potential, which is, if not analytic, then infinite.
Ilya, stop. You would like to give me a counter example? I am not mathematician at the moment. So you can't. I know also counter examples.
No, of course, if you simply say that you are a believer in something, then I cannot argue with that. But
But I think we should stop.
Yeah.
there are arbitrary. This is. I'm just saying that this is still not an explanation, because it can be arbitrarily smooth.
I do not pretend. I am saying from the very beginning that I do not pretend. I said this already to Jan and to Shmuel. Then I'm saying to you. I do not pretend, Ilya.
Well, when you were arguing with them, I said, of course, you're right. Yeah.
Okay.
No, it's a miraculous thing. And,
Of course.
the proof, as we saw, is a lot of work, and it's a deep thing.
And to give a justice, I would like to say that our first proof, which was given 30 years ago, was much more complicated and technically involved. It was for the continuous Schrödinger with Markov potential, etc., etc. The main idea of this proof that I gave you, the spectral averaging,
white noise?
Could I finish? So the spectral averaging, was invented by Kotani. In fact, it was invented much before in spectral theory. Aronshine, Biermann in 40s and 50s invented, but for another purposes. But Kotani found that it is useful for this, and this is precisely his argument. As for this part, this was joint ideology by Kotani and Wagner, because Wagner was the first realizing that there are cases when density of states is smooth. So this is shortcut proof. This is due to Kotani mainly for localization.
What is Markov? Potential white noise?
White noise is not Markov. It is independent at every point. It's trivial case of Markov.
Okay.
Markov potential, it's correlated potential.
So for all Markov potentials you prove it.
Not all, but a certain class. Yeah, of course. This was our proof. By the way, the potentials very, very smooth, very, very smooth. And nevertheless, this is why I had this argumentation with Lifshitz. Okay.
Okay, let's thank the speaker.